There is a radio signal moving through the darkness right now. It is almost impossibly weak. It has traveled farther than anything humanity has ever sent before, crossing a distance so enormous that the signal needs nearly an entire day just to reach Earth. And when it finally arrives, it does not sound like a voice. It sounds like almost nothing. A pattern of radio energy buried in the noise of space. But inside that faint signal is a message from a machine that was launched before the modern internet existed, before the first reusable space shuttle flight, before most of the technology surrounding us today had even been invented. For nearly half a century, it has continued moving outward. And now, every transmission matters. Because the machine sending them is running out of power, the people listening know that one day, perhaps sooner than anyone wants to admit, the signal will stop. There will be no dramatic explosion, no final photograph, no visible ending, just silence. And that is what makes the latest chapter of Voyager 1 so unsettling. Because NASA is no longer simply asking how to keep the spacecraft operating, they are asking how to keep a machine alive when almost every part of it is older than the people now responsible for it. This is the real story of Voyager 1's final transmission. Voyager 1 began its journey on September 5, 1977, launching from Cape Canaveral, Florida, on a mission that was never supposed to last this long. The original plan was comparatively simple: fly past Jupiter, fly past Saturn, study the planets and their moons, then continue outward. Nobody designing the spacecraft in the 1970s could have reasonably expected that nearly 5 decades later, engineers would still be waiting for its radio signal. Nobody expected it to become the most distant human-made object in existence, and almost nobody expected it to cross the boundary between our solar system and interstellar space. But Voyager kept going. It survived Jupiter, it survived Saturn, it survived decades of radiation, freezing temperatures, failing components, aging electronics, diminishing electrical power, and a communication system operating across distances that are difficult to comprehend. And eventually it reached somewhere no spacecraft had ever reached before. On August 25, 2012, Voyager 1 crossed the heliopause. That was not simply another milestone. The heliopause is the outer boundary of the Sun's heliosphere, the enormous bubble created by the solar wind and the Sun's magnetic field. Beyond it lies interstellar space. For the first time, a human spacecraft was directly sampling the environment between the stars. But there was a problem. Voyager was never designed for this. Its instruments were built in an era when engineers were thinking about Jupiter and Saturn, not decades of interstellar exploration. Its computers had tiny amounts of memory by modern standards. Its transmitters were incredibly weak compared with almost anything we would recognize as modern communications equipment. And its power source was slowly dying. The spacecraft does not carry solar panels. That would be almost useless at its distance from the Sun. Instead, Voyager uses radioisotope thermoelectric generators, RTGs. They produce electricity from the heat released by radioactive decay. And radioactive decay has one unavoidable characteristic: it never negotiates. Every year, the available electrical power declines. NASA has estimated that the spacecraft lose roughly 4 watts of power each year. 4 watts may sound insignificant. It is not. On Earth, 4 watts is almost meaningless. Inside Voyager, 4 watts can determine whether an instrument remains alive. So NASA has been shutting things down, one system at a time, one heater, one instrument, one electrical load after another. Every decision is a trade: keep the spacecraft warmer and lose power somewhere else. Keep an instrument operating and sacrifice another. Protect communications and reduce scientific observations. There is no unlimited reserve. There is no replacement battery waiting somewhere. There is no repair mission. Voyager is alone, more than 15 billion miles from Earth. And the distance creates another extraordinary problem. When NASA sends a command, the spacecraft does not receive it immediately. The radio signal travels at the speed of light. Even at that speed, the journey takes more than 23 hours. Then Voyager has to execute the command. Then its response has to travel all the way back. Another roughly 23 hours. A simple question can therefore require almost 2 days to receive an answer. Did it work? Did it fail? Did something else break? Nobody on Earth knows immediately. They wait. And while they wait, Voyager continues moving. This is why communication with Voyager has always been more than simply sending instructions. It is a conversation conducted across a distance so large that every exchange is separated by nearly 2 days. And that conversation has become increasingly fragile. The first major warning signs appeared long before the spacecraft reached its current condition. Voyager has suffered multiple technical problems throughout its extended mission, but perhaps none revealed its vulnerability more clearly than what happened in late 2023. In November of that year, Voyager 1 suddenly began sending back a stream of data that was essentially useless. The spacecraft was still communicating, the signal was still reaching Earth, but something inside the machine had gone wrong. Instead of receiving meaningful engineering information and scientific measurements, NASA was receiving a repeating pattern. The spacecraft was talking, but nobody could understand what it was saying. That distinction became critical. Voyager was not dead, it was trapped. The Flight Data System, or FDS, was responsible for collecting information from the spacecraft and packaging it for transmission. If that system could no longer properly communicate with the telemetry modulation unit, the radio signal could continue while the useful information disappeared. It was like receiving a telephone call from someone whose voice had been replaced by static. NASA engineers began working backward. They could not simply open the spacecraft and replace the computer. They could not upload an enormous modern software package. They could not reboot everything simultaneously. Every command had to be carefully designed for hardware that was almost 50 years old. And then there was the distance. A command could take more than 22 hours to reach Voyager. The response could take another 22 hours. One mistake could consume nearly 2 days. So engineers began looking for clues inside the strange signal. Then, in March 2024, something unexpected happened. NASA sent what engineers called a poke to the spacecraft. The idea was simple: try to make the damaged computer behave differently. If Voyager could produce even a slightly different response, engineers might be able to determine what was happening inside. The spacecraft answered, and what came back contained something astonishing: a readout of the FDS memory. The data was still difficult to interpret, but it gave engineers something they desperately needed: a view into the spacecraft's internal state. They began comparing the information against older memory records. The mystery slowly narrowed. A small portion of corrupted memory appeared to be responsible for the problem, and this was where the story became almost absurdly difficult. The spacecraft had been launched in 1977. The engineers working on it in 2024 were solving problems that its original designers could never have anticipated. They were consulting decades-old documents. They were examining old software. They were reconstructing the architecture of a computer that had been operating since the Carter administration. And because Voyager could not simply be upgraded like a modern computer, the team had to find a way to work around the damaged memory without destroying something else. Eventually, they did. By April 2024, Voyager 1 began returning usable engineering information again. Then, in May, science data started coming back from its instruments. The spacecraft had survived. Again. But that rescue revealed something more important. Voyager was no longer simply an old spacecraft. It was becoming an archaeological object that still happened to be functioning. Its engineers were operating machinery whose design philosophy belonged to another technological era, and every success was becoming harder to repeat. Then came another warning. In October 2024, Voyager 1 experienced a communications problem that forced NASA's engineers to search for another way to hear it. The spacecraft's fault protection system had been triggered. The system is designed to protect Voyager when something goes wrong, especially when electrical power becomes dangerously low. The spacecraft shut down its primary X-band transmitter. That alone was serious. But Voyager had another transmitter, the S-band transmitter. There was just one problem. Voyager had not used it to communicate with Earth since 1981, more than 4 decades, and the signal was significantly weaker. NASA engineers were not even certain that Earth would be able to detect it across the enormous distance. Then they listened, and they found it. A faint signal was still coming home. It was another reminder that Voyager was not simply surviving through good luck. It was surviving because engineers were constantly finding ways around problems that should have ended the mission years ago. The X-band transmitter was eventually restored. Voyager returned to regular operations. But the episode exposed a deeper problem: power. Because the transmitter had not failed randomly, Voyager's fault protection system had reacted to the spacecraft's increasingly limited electrical supply. The spacecraft was running out of energy, and the situation was getting worse. The power comes from plutonium. The plutonium does not suddenly stop working. It fades. Slowly, predictably, relentlessly. That means NASA can forecast the general direction of the mission. But forecasting is not the same as knowing exactly when the spacecraft will stop. Aging components behave unpredictably. Temperatures change. Electrical systems deteriorate. Heaters consume power. Thrusters become less reliable. Instruments require energy, and every watt becomes more valuable. NASA has therefore been shutting down science instruments to extend the life of the spacecraft. In February 2025, the cosmic ray subsystem aboard Voyager 1 was turned off. The instrument had spent decades measuring energetic particles in deep space, but keeping it alive required power. So NASA made the decision. The instrument would go silent, not because it had failed, because Voyager needed the electricity somewhere else. That is an important distinction. The spacecraft is not dying because its instruments are suddenly breaking one by one. Some of them are being deliberately turned off because there is not enough power to keep everything operating. Then came another extraordinary problem: thrusters. Voyager needs tiny thruster firings to keep its antenna pointed toward Earth. That may sound simple. It is not. The spacecraft is billions of miles away, moving through interstellar space. Its communication antenna must remain pointed with incredible precision toward Earth. If it drifts too far, NASA could lose the signal. And Voyager's original thrusters were never designed to operate for nearly 50 years. Over time, residue began accumulating inside the fuel tubes. The passages became increasingly vulnerable to clogging. NASA engineers had already switched to backup thrusters decades earlier, But even those backups were aging. In 2025, engineers attempted something that sounded almost impossible. They revived a set of thrusters that had been considered unusable since 2004. They did it because the active thrusters were becoming vulnerable, and they had to be careful. The spacecraft had heaters that had been turned off to save power. If the thrusters fired while certain components were still too cold, there could be serious consequences. So engineers had to reconstruct a delicate sequence of commands. They sent the instructions. Then they waited. The signal traveled more than 23 hours. Eventually, the spacecraft responded. The engineers watched the data. And within minutes of the relevant sequence, the temperature of the thruster heaters rose. The dormant thrusters had come back. A system believed to be dead was alive again. Another rescue, another extension, another few pages added to a mission that should have ended decades ago. But the biggest threat was still waiting: electrical power. In April 2026, NASA made one of the clearest statements yet about Voyager 1's future. Engineers shut down the low-energy charged particles experiment known as LECP. The instrument had operated almost continuously since Voyager launched in 1977, nearly 49 years. Think about that. An instrument designed in the 1970s had spent almost 5 decades traveling through space and measuring particles from an environment no human had ever directly explored before. And now NASA had to turn it off. The reason was brutally simple: power. The spacecraft needed breathing room. NASA estimated that shutting down LECP could give Voyager 1 roughly another year of power margin. That is how the mission is being managed now. Not in decades, not in years, sometimes in fractions of a year. Engineers are trying to buy time, and that is where the phrase final transmission becomes more complicated. The final transmission may not arrive as a dramatic message. There may be no moment when Voyager suddenly announces that it is dying. Instead, the end may arrive through a sequence of increasingly difficult decisions. One instrument disappears, then another, a heater is turned off, a transmitter becomes too expensive to operate, a computer develops a fault, a component can no longer maintain its temperature, a thruster loses reliability. Eventually, there may be too little power left to maintain communication, and when that happens, Earth will listen. But Voyager may not answer. The strange thing is that the spacecraft could continue traveling for millions or even billions of years after its radio signal disappears. The machine would not suddenly stop moving. Its trajectory would continue. It would drift outward, silent, carrying a message from Earth into the darkness. The golden record. That record is perhaps the most haunting part of the entire Voyager story. The spacecraft carries a 30-centimeter gold-plated copper disc containing sounds and images from Earth. Greetings in dozens of languages. Music, sounds of nature, human voices, photographs, information about our planet, instructions for how the record might be played. It was designed as a message to anyone who might someday encounter Voyager. Not necessarily soon, not necessarily even within the lifetime of humanity. It was an act of cosmic patience. The spacecraft might outlive civilizations. It might wander through the galaxy long after Earth's cities, languages, nations, and technologies have changed beyond recognition. And now the irony is becoming sharper. The golden record was built to survive for an almost unimaginably long time. The electronics carrying the message may not. The spacecraft may eventually become a silent artifact. The record could remain intact. The radio transmitter could be dead. The instruments could be frozen. The computer could be powerless. And yet the physical object would continue moving. That raises a question nobody can answer. What is Voyager's mission when it can no longer communicate? For NASA, the answer is scientific. As long as the spacecraft can return measurements, it is useful. It is studying interstellar space. It is measuring particles and magnetic fields. It is providing information about an environment that no other spacecraft has reached in the same way. But there is another meaning. Voyager represents something that has become increasingly rare in modern space exploration: patience. The spacecraft was launched in 1977. The people who designed it knew that its most extraordinary discoveries might come decades later. They built something that did not need immediate results. They built something that could wait. And that patience has paid off. Voyager 1 became the first spacecraft to enter interstellar space. It discovered new details about Jupiter and Saturn. It observed Saturn's atmosphere and rings. It helped transform our understanding of the outer solar system. And later, far beyond the planets, it began measuring the environment between stars. That environment is not empty. It contains particles, magnetic fields, radiation, plasma, waves. Voyager has shown that the boundary between the sun's influence and interstellar space is more complicated than a simple wall. The heliosphere is dynamic, its outer region changes, particles move, magnetic fields interact, and the spacecraft is still providing information from a place where almost nothing else can. But now, the mission has entered a different phase. The science is still important, yet the act of keeping the spacecraft alive has itself become a scientific and engineering experiment. NASA engineers have to understand a machine whose behavior has been shaped by nearly 50 years of radiation exposure, thermal cycling, aging electronics, mechanical wear, and accumulated modifications. The spacecraft has become its own environment, and every Every decision now requires historical knowledge. Imagine trying to repair a computer that is 15 billion miles away, using software created before you were born, with no physical access to the machine, while every command takes almost a day to arrive. That is the situation, and there is no backup Voyager waiting nearby. There is no second attempt. There is only the one spacecraft. That is why every successful recovery feels extraordinary. When NASA restored usable engineering data in 2024, it was extraordinary. When engineers brought back dormant thrusters in 2025, it was extraordinary. When NASA continued operating the spacecraft while turning off instruments to conserve power, it was extraordinary. And when the team shut down LECP in April 2026, it was not simply the end of an instrument. It was another reminder that the mission is moving toward its final chapter. NASA is not giving up. Quite the opposite. Engineers have been developing a more ambitious energy-saving strategy for the Voyagers. They call it the Big Bang. The name sounds dramatic, but the concept is practical. The goal is to replace or switch off groups of power-consuming devices so that the spacecraft can preserve enough heat and electrical energy to continue operating. The plan reflects the reality of Voyager's condition. There is no way to add new power. There is no way to refuel the spacecraft. There is no way to send a mechanic. The only available resource is the power already inside the machine. So NASA is learning how to spend it more carefully. That may be the final great engineering challenge of Voyager, not how to make it faster, not how to make it smarter, how to make every remaining watt count. And this is where the story becomes much larger than one spacecraft. Voyager 1 is now more than just an exploration mission. It is a message about technological longevity. Modern electronics are designed around rapid replacement. Phones become obsolete, computers are upgraded, satellites are replaced, software changes, hardware becomes incompatible, but Voyager operates according to a completely different philosophy. Its engineers cannot replace anything, so they adapt, they reinterpret, they conserve, they find unused capabilities, they revive dormant systems, they work around corrupted memory, they use old documentation.